And the unique thing about inverses, when we have, if matrix A and matrix B are inverses, this commutative property that we talked about does not hold for multiplication. Something weird happens with inverses. So when we do A times B or we do B times A, if they are inverses, we actually do get the same product, and that product is quite unique. It's called the identity matrix. So I am giving you two matrices that are inverses. A and B are inverses of one another. So ladies, I would like you to find the product of A times B. And gentlemen, I would like you to find the product of B times A. Normally, these products are different. Let's see what happens.
They're the same.
We already talked about spoiler alert. Don't
Oh
do
my
that.
bad, I'm sorry.
I don't want to do it anymore.
I do that a lot. I'm sorry, Colin.
Okay.
Well, if they're the same, we'll just let the ladies do it.
Yeah.
Your word's good enough for us.
You're a precious.
Okay. So ladies, what did you get? All right.
Oh, there it is.
Okay.
1,
The
0, 0.
identity matrix is 1, 0, 0, 1. Okay. So we should have gotten 1, 0, 0, 1. All right. Let me take a timeout, and I have to climb on my soapbox real quick. Don't you ever believe me. You question everything anybody says to you. So do not sit there blindly and accept that everything I tell you is the truth. You question and you test everything. You don't blindly follow. That would make you sheep. Okay? You are not sheep. So when I ask you to do this, you don't sit on your loins and wait for somebody else to tell you the answer and accept it as truth. No.
You preach.
All right, crawling off the soapbox.
No, be your own leader.
And gentlemen,
1,
the-
0, 0, 1. But isn't that
okay, so we talked about yesterday, multiplication is not commutative with matrices, and it's not. This is the only special case where we can change the order in which we multiply matrices and we get the same result. This result is very special. This result is called the identity matrix. Now, an identity matrix is quite unique in the fact that any matrix I take, let's say I try a new matrix, matrix C, and I call it 2, 5, -3, 1, and I multiply C by the identity matrix. You'll be able to tell it's an identity matrix because with an identity matrix, we have ones going down the diagonal and zeros for every other element. And that is what we name the a matrix as the identity matrix. We can have a 2 by 2, a 3 by 3, a 4 by 4. As long as we have ones going down the diagonal and zeros in every other position, then it's the identity. And anytime we multiply a matrix by the identity matrix, we end up with the original matrix. And let's prove it, because we don't just blindly believe. 2 times 1 is 2, plus 0 is 2. Okay, those of you that say, I just believe, that helps me know where to place you next year in mathematics. That lets me know what you're capable of and where your limitations lie, so I can give an accurate placement for you next year. All right, 2 times 0 is 0, plus 5 times 1 is 5. -3 times 1 is -3. 1 times 0 is 0. -3 plus 0 is -3. 0 plus 1 is 1. Okay, so here we have another example that shows when I multiply a matrix times the identity matrix, it does not change the matrix. Okay, and this is critical for where we're going from here. This is very important to understand that when we multiply matrix inverses, we get the identity, and when we multiply a matrix times the identity, the result is the original matrix. Yes, Nick?
What if it's like a solid row or a column?
Then that is not the identity matrix, and your result will change.
So
So it has to be the diagonal. So I said this is the identity matrix for a 2x2. If we had the identity for a 3x3, it would look like this. Ones down the diagonal, zeros everywhere else.
is it always goes?
Okay?
So you can't do that from,
Yes, it always goes down from left to right.
but you can't do that like a 3x1 or 1x3 one.
Correct. The identity matrix is for square matrices. All right?
So there's no inverse on this.
Correct.
What about if you multiply like the identity times the matrix?
Try it. Okay, so Dalton's questioning. What happens if I do this? Let's do it. 1, 0, 0, 1.
You get the identity matrix.
No, it's the same thing. Yeah, I figured it.
Yeah, it's the same thing.
Okay, so we get 2. We get 5.
No, you get the inverse of C.
We get -3. And we get 1.
It's the exact same thing.
I tried my best.
Will that always happen?
We know where you're gonna
So
be
CI equals I.
Yeah,
I
then
see.
we know where you're gonna be placed.
Yeah, I think
How do you
Oh,
like
this is
write
pretty-
the
At least
inverse?
you know.
Like up there where it's like flipped and opposite sides?
How do you find the inverse? Oh, we're going to do that in just a minute. I'm going to teach you the process to find the inverse. Now, so the identity matrix is like the multiplicative identity. Remember when we studied operations with real numbers, the number 1 is the multiplicative identity because we can multiply any real number by 1 and we get the real number we started with. Well, the multiplicative identity for matrices is the identity matrix. Because any matrix that you multiply by an identity matrix gives you your original matrix. So it's the same terminology, we've just used it with matrices. Okay, now we're going to learn to find an inverse, but a step to finding an inverse is finding what's called a determinant. And we're going to use the determinant for matrices in a couple different ways. Now, we're going to start with just a 2x2. We're going to do a 2x2 and a 3x3 without technology. And then once we've mastered that, we will bring in technology to do more complex things. And by technology, I mean your calculators. Okay? Matrices are quite helpful in taking organized data and performing operations with it quickly and accurately, especially with the use of technology. But we have to understand what our calculators are doing before I let you do it on the calculator. So the first thing we're going to find is a determinant of a 2x2. So we have to start off with a square matrix. And so if I say matrix A is represented by A, B, C, D. The determinant of A, and this is one way I can ask for the determinant of A, or, do you see this looks like really big absolute value bars around a rectangular array, around the matrix. This is another way of me asking you to find the determinant. Well, the determinant is pretty simple. It's just the difference of the cross products. So, you would do A times D, and subtract from that B times C. Okay, so do you see in number 1, I have asked you to find the determinant because it's no longer the brackets, it's like the really big absolute value bars. But around an array of numbers, that's asking you to find the determinant. So what we would do is 2 times 9 minus -3 times 4. The determinant of this matrix is 30. You try number 2.
Oh, wow.
That one seems good.
Oh, you go.
So what's like the point?
Okay. The determinant has lots.
Gosh, this is, I don't know how to do that. So I'm constant. 44. Yes.
Dividing 3 minus
Yeah, you 44 as well. I don't
Yeah.
understand.
Well, I haven't taught you how, so you shouldn't understand yet.
That seems actually not good.
Okay, so here, you got 9 minus 4. So you found that the value of this determinant is 5, correct?
Yes.
Okay, so that's what we would do with a 2 by 2. Very simple, nice, and then comes the 3 by 3.
I don't think we
Okay, so let me erase this and we'll start over together so it's not a little mind-boggling to start with. So if we had a 3 by 3, and so matrix C, and I labeled these with variables on purpose so that we can see what this will look like no matter what type of numbers are in here. How would we find the determinant? Okay, so the cross product thing isn't really going to work for us here. So what we do to find the determinant is we would pick a row. And then as we pick the row, like let's say we picked this row right here. So we would start off with an A, a B, and a C. And then when we pick this row, it actually eliminates things for us. So the A, if we pick the A is in this row and this column. Do you see it leaves this 2 by 2? Okay? So it would be A times the determinant of this 2 by 2.
What 2 by 2?
The one that you can still see.
Oh, okay.
Oh, wow.
Okay? And then we move over to that same row where B is. So B, when we choose B, it eliminates this column. So what does it leave us for the 2 by 2? D, F, G, I. And then C, we scoot on over. And this would leave us D, E, G, H. Now, there is a lot of flexibility with this method. I don't have to start with the first row here. I could choose any row to start with. So if I chose to start with this row, what would I multiply D by? The determinant of B, C, H, I, right? Now, why would I ever choose a different row than the top one?
If there's zeros.
If there's zeros.
I'm smart.
Okay? Now, the last thing we have to talk about are the signs. And this is kind of strange. So, to find the sign that goes in front of A, B, C, actually any of these, what you do is you take the position and add the position together. So, if this is position 1, 1, right? So, the coefficient of A would be -1 squared. 1 plus 1. What is -1 squared? Positive.
Why?
Okay? We have to figure out the sign that goes in front. That's what we're doing. This is position 1, 2. So the coefficient for B here would be -1 to the 1 plus 2. So it's going to be negative. And then what's this one going to be? Positive. What you're going to discover is the signs just rotate. And if you go home and Google this, somebody may just say, oh, the signs just swap. And they do, but there's a reason they do.
So
Okay?
it's always going to be -1 to the I plus G. Or I plus J.
Yeah. And that's what your coefficient is. -1 to the I plus J. IJ represents the position, row column. So this is 2, 1, right? This is 2, 2. This is 2, 3. So -1 to the 5th, that's why that's negative.
Oh.
negative 1 to the 4th, that's why that's positive.
But we don't actually use it. So it'll always start positive. We only use
Okay,
A, B, and C.
now, in this example 3 that I'm asking you to find the determinant of this 3 by 3, I would choose the second row because the second row has a 0. So I'm going to choose this second row. Now I have to know the signs because this is position 2, 1. This is negative 1 to the 3rd. So that's negative 3. Who cares what the sign in front of 0 is? Because 0 times anything is 0. And then finally, this is position 2, 3. So it's going to be a negative 1 there. Now, let's see if we can figure out what are my 2 by 2s. So right here, this is the row I've chosen. So when I do the 3, what does it leave me?
2, 1, negative 3,
2, 1, negative 3, 2. Okay? Now the 0 doesn't really matter, does it?
No.
I'm not even going to write it. Okay, yes I am. It really doesn't matter what it is because it's 0 times that. So we're not actually going to determine what that is algebraically. And then finally, what is the remaining? 4, 2, negative 2, negative 3. So this case, we don't even have to do that because it's 0 times something. So here, this becomes negative 3 times 4 minus negative 3. This is negative 1 times negative 12 minus negative 4. So this is negative 3 times 7, negative 21. This is negative 1 times negative 8, positive 8. So the result is negative 13.
Wait, how'd you do that one step? Parentheses.
How to do this? Okay, so I went back to the cross product. 2 times 2 is 4 minus negative 3 times 1 minus a negative 3 beta plus.
I use this a different row better, different answer, so that's what's happening.
If you use a different row, you should definitely get the same answer. Which row did you use?
The top one.
The top one. Okay, so we have 4, negative 2, positive 1, right?
Yeah.
And then you have 0, 1, negative 3, 2. And then we have 3, 1, negative 2, 2. And then you have 3, 0, negative 2, negative 3. Alright, so we get 4 times 3.
Negative 3.
But it's minus the negative?
Oh, yes.
Wait, say what?
It would be 0 minus. Oh, never mind. I just messed up on this.
Okay.
I got it.
You good?
Yeah, I got it.
Okay. So, yay, we found it. Alright, so we should, and we will get the same result no matter which row we use, as long as we get all this arithmetic in here right. And arithmetic can get us sometimes. Alright, now, we did say you can find the determinant by the difference between the cross products. That's what we did on the 2 by 2. And then we said we don't want to use that with this method because we're cross products. I only have this one cross. But what we can do, and what I didn't show you to begin with, is we can repeat their first 2 columns.
Repeat them for what?
Okay? So that we can continue with our diagonals.
What?
Okay?
You
Alright,
lost me.
so I'm still finding my cross products.
Why? The highlighter.
Is this just another way to do it?
Mm-hmm.
Wait.
So if you had like a 4 by 4, would you repeat the first 3 columns?
If we had, yeah.
What determinant are you trying to
So what do you do with those numbers?
Okay, so what do? We do a product 4 times 0 times 2 is 0 plus 2 times 1 times negative 2 is negative 4 plus 1 times 3 times negative 3, negative 9. And then we subtract from that the other direction.
That way. Yeah, oh my god.
Wait, how did you get 0 for the first
I mean, this
one?
is faster than the other way.
It is.
Yes.
Oh my god. Oh my god.
Okay,
If I had a highlighter in my test, I would do that.
any diagonal that has a 0 in it, the product has to be 0. That's how I got a 0 here. Because anytime there's a 0 in your diagonal, the product has to be 0. So 0 plus negative 12 plus 12. So what is negative 13 minus 0? Negative 13. Oh,
So-
look at that.
So
Look at that.
the only reason you're dividing the first or the 2 rows is so like you can see what they match up with. 'Cause
Right.
it's like the matrix. It's not like that.
Right.
It's like,
Right. I'm not really changing the matrix. I'm just making it easier for me to see.
Yeah, hold on.
Yes.
So you're ignoring my 3 to 0 pretty much?
Right. If they're not in that diagonal, they're not part of that operation. Okay.
Which one do you like? Whenever I got
Guys, if I were you tonight, I would do at least one using this method and at least one using that. I would try both.
Okay.
I would try both. Okay. Now, the reason we learned about determinants is because we have to use determinants to find inverses. There are also some other clever uses for determinants that we'll discuss after we learn how to correctly find them. Okay? So, we're going back to a 2 by 2 because the 2 by 2 is the matrix that we're going to ask you to find the inverse for without the aid of technology. So how do we find the inverse for a 2 by 2? If we have matrix A, which is A, B, C, D, the inverse is 1 over the determinant, which is why we just figured out how to do that. And then, if you'll notice, in this diagonal, we will switch the 2, and in the other diagonal, we will change the signs. Determinant. This is the word determinant. DET.
What is this? New sheet.
Okay. I'm going to have to start a rule to where you can't say what until I've finished an example. Because y'all are being a little dramatic about math that's not that scary. So, no what's allowed until we've done an example. It's like it's 9th grade boys in here. Yes, ma'am.
So, like at the beginning when we said A and B were inverses, this is how to find B.
Correct. Very good. So, this is matrix W. And we're going to find the inverse. Oh, does this symbol look familiar? Yes. So this is the inverse of matrix W. So let's go through this procedure. We have to do 1 over the determinant of W. So let's find the determinant of matrix W. It is 2 times 7 minus 3 times 5. Oh, I picked myself an easy one. Negative 1. The one I picked for you is not as easy. Right? So, that's how I start. 1 over the determinant. Okay? So I created this nice integer scalar for me to multiply by in just a moment. Alright? And then what I do is I switch this major diagonal, switch those 2 elements, and then I change the signs of the others. Now, this simplifies to negative 1. And negative 1 through here will just create the opposite of all my signs. So, now, how can I prove that I have done this correctly?
You multiply them and it should give you 1, 0, 0, 1.
You are correct. Try it. See how we did.
Good job.
You have to prove it every time.
Good question.
What?
You have to prove it every time.
No.
I want to coach you that.
No. And that's a good question. I'm not going to ask you to prove that they're inverses every time, but if you're taking a quiz and you have enough time left and you want to be able to check your work, this is a great way to do it.
Oh, what that is. I get it. It's just confusing.
Oh, so the image is.
All right, negative 14 plus 15 is 1. 10 minus 10 is 0. Negative 21 plus 21 is 0. 15 minus 14 is 1. It works. It works. Okay? Now, this is the U try.
It's actually kind of easy. Oh, God.
This is the U try.
I got this.
Oh, is that 12?
Okay, please put comments like, oh my goodness, which is what you almost said, with what? We shouldn't say until after we've tried. There's all my work, and you can see your problem. So first you find the determinant. One over the determinant.
So you have like fractions.
You do.
So how would that work if it's on the negative?
Okay, so your determinant is negative 4. So what this means is when we're done switching things around, the 3 and the 12, and changing the signs, we have to multiply these by negative 3/4. Which all that means is we have negative 1/4. So we get negative 3/4, positive 2, positive 5/4, negative 3. Okay? Now, my last question to you is, do all 2x2s have an inverse?
Yes.
No.
Yes.
You're asking that question.
They have to.
No, what if it's 0, 0, 0?
Well, then it's inverse is 0, 0, 0, 0.
That doesn't mean there's no 1, 0, 1.
Or,
They all have
so it doesn't, with a hash.
Can you
No,
help with 0,
they
0,
don't.
0 with all
They
that?
do.
I mean, unless you know.
What's
the
No.
answer? No.
Yes.
Final
Yes.
answer?
You all two what you said.
Okay,
Final answer, no.
what's more important to me, the answer or the how and why?
How and
How and why? How and why is what I want to hear tomorrow.
Oh, that's homework?
In
So we don't have
addition,
any other homework.
no. You do have homework, and the directions have changed on your homework. So let's all make sure we can look at this. Let me see if my website will open up correctly now. Do not follow the directions on the sheet. We're finding inverses.
What?
So
Well-
the instructions are on the website.